Okay, guys, so let's continue our discussion that we started last time. So last time we were talking about extrema, extreme values for a function. So that means minimum and maximum values. And remember that this could be the relative or absolute. Okay, so we were talking about the fact that if we wanted to find relative extrema, and you know, if you're gonna look for some for relative extrema, you need to look for critical points of a function because we saw a theorem that says that if a point is a relative extrema, then it must be a critical point. And I remind you that a critical point or critical number is a value in the domain of the function for which the derivative is either zero or undefined. Okay, so now I would like to uh, talk a little bit more about how to actually find those points, but before the relative extrema. But before we get there, let's pause and let's talk about absolute extrema and a very important theorem which is called the extreme value theorem. All right, so let me remind you the definition. So suppose that we have a function that's defined on an interval I containing a point C. Then remember we say that f of c is the minimum of f on that interval if f of x is always greater than or equal than f of c for all x in I. In other words, if the value of the function at c is the smallest possible on the entire interval. So similarly, we say that f of c is the maximum of f on I if f of x is less than or equal than f of c for all x in I. Okay, so the value of the function at c is the highest possible value that you can obtain inside that interval. That's what it means to be a minimum or a maximum on an interval. And so what's an absolute minimum or absolute maximum? Well, when we can take this interval I to be the entire domain. So if I equals the domain of the function, then the above refers to absolute minimum and absolute maximum, respectively. Okay, so in other words, if the function has an absolute minimum, if there is a point at which the value of the function is the smallest for any x. Okay, so it's for all x, f of x is greater than or equal than f of c. And it's going to be an absolute maximum if f of x is less than or equal than f of c for all x in the domain. In other words, f of c is the highest possible value that you can get on the entire function. Okay, so the question now is, given a function, how do we figure out absolute maximum, absolute minimum? And the point is that, this really depends whether some functions have absolute extrema, other functions don't. Like, for example, think about a line, y equal x, simplest one, y equal x. This line doesn't have an absolute maximum or minimum, okay? So not every function has an absolute maximum or minimum. So what do we mean by finding this? Typically, you want to find absolute maximums or minimums for a function on a given interval, okay? So now the question is, are we guaranteed to always have a maximum and a minimum for a function inside a given interval? And then the answer is, well, yes, as long as the interval is closed and the function is continuous. Okay, so this is a very important theorem. This theorem is called the extreme value theorem. Okay, and it says what you can see here. If you have a continuous function on a closed interval AB, then f has both a minimum and a maximum on that interval. Okay, so I'm not gonna take time to prove this statement because actually the proof of this statement goes a little bit beyond what we have discussed in this course. Okay, it requires some notions of topology and so on that we have not discussed. And that's something that you do in all courses if you study mathematics later on. Okay, but nevertheless, it's a very important theorem and we need to keep it in mind. And we're going to use this theorem to be able to find maximum and minimums of a function on a closed interval. Okay, so let me make a remark here, and the remark is that the fact that the interval has to be closed is very important. So it's very important to require that the interval is closed. Otherwise, so let me give you an example. So think about the following picture. So I'm just gonna draw a line. As you know, lines are continuous, right? So let's draw a line segment. I don't know. Let's say from 1 to 3, and let's say this is 1 and 3. So this is a piece of the function y equal x. Okay, but let me do open circles here, and then I'm gonna draw the line segment containing these 2 points. So this is a piece of the function y equal x. So if you want here, this is the function f of x equals to x, and then we're looking at the interval 1 to 3, but this time this is an open interval because I'm not including the endpoints. And here, in this case, this function is continuous on this interval, so it satisfies part of the hypothesis of the theorem. It is just that it doesn't satisfy the fact that we have a closed interval, because we have an open interval here, but the function is continuous, but it doesn't have a maximum, it doesn't have a minimum. Okay, so f has no maximum or minimum on the interval 1 3, because I mean, no matter what point on the graph you pick, you can always go slightly higher. The maximum will be at 3, but it's not included. Okay, so anything that's less than 3, you can always go a little bit higher. And similarly with the minimum will be at 1, but because that point is not included, the point 1 1, then any value that you pick that's slightly bigger than 1, you can always go slower, still within the same interval. So that's why it's very important to require that we have a closed interval. Okay, so let's do an example. Here is a function. It's a parabola, right? X squared minus 4x plus 5. That's a quadratic function. It's a continuous function everywhere. In particular, if I give you a closed interval, it will be continuous. So it has to have a maximum and a minimum. So let's find them. Okay, so find the maximum and minimum values of the function on the interval -1, 3. So how do we do something like this? The good thing, the idea is that we want to have a systematic way of answering questions like this by working just with the formula. Okay, but that's what we're going to try to do now. But to get an idea of what we need to look at, let's first do this another way, which is let's take advantage of the graph. We know how this function looks like. This is a parabola, and we know everything about parabolas. So let's graph this function, let's answer this question visually, and then from that we will be able to extract some ideas that will allow us to see how to actually you know systematize this process of finding, do it in a systematic way, how to find maximum and minimums on a closed interval. Okay, all right, so let's do this. Solution. Okay, so we have let's see, we have the function f of x equals x squared minus 4x plus 5. So in this case, what we're going to do is we're going to try to graph this function. Okay, so we know that this is a parabola, and then, for example, can we factor this? Mhm. 5 and 1, and none of those work. So no. So I'm gonna go ahead and and complete the square. So let's see, this is the same thing as x squared minus 4x, then the negative 4 divided by 2 on squared. So it's going to be negative 2 squared, which is 4. So I'm going to put it here plus 4. We have the 5 in there, and then subtract 4. So that becomes x squared. Okay, yeah, let me write the whole thing. Square minus 4x plus 4 plus 1. So f of x equals x minus 2 squared plus 1. Okay, so by doing this, we can then very easily graph the function. So the vertex is the point 2, 1, and then we know it opens up. So we are ready to sketch the graph. By the way, you can also find the vertex with the formula, the x is negative b over 2a. And then once you know the x of the vertex, you plug it in to find the y. Let's see. Here is x, here is y. So negative 1, and let's say here is 1, 2, 3. Let's do one more. 4. Okay, so 2, 1. That's what the vertex is. Then the y-intercept is going to be 5. So 2, 3, 4, 5. So we have to go through this point. And then by symmetry, the line of symmetry is x equal 2. So 2 units to the right. So that's a 4, 5. We're going to have another point on the parabola. Okay, so let's sketch. So first I'm going to do it like this. And then I'll change the color. Okay, now this is the graph of the function f. However, we're not really interested in the entire graph. We are only interested in what happens from negative 1 to 3. So let's do that. So let's see, when I plug in negative 1, what's f of negative 1? So that's going to be 1 plus 4 plus 5, so equals 10. So, okay, so that's 6, 7, 8, 9, 10. Okay, so that's way up there. So let's just say that that's going to be here, okay? So this is the point negative 1, comma 10. All right, so we only care about what happens from negative 1 all the way up to 3. So what's the value of the function at 3? That's 2. Okay, so up to here. So I'm gonna change the color. So in other words, we only care about this piece of the function from negative 1 to 3. This is what we care about, what's written here in red. Okay, the rest is not part of our considerations. Why? Well, because we were given that interval from negative 1 to 3. And then looking at this picture, then, looking at the graph, we can easily answer the question now. So on this closed interval, we do see an absolute maximum, and we also see an absolute minimum. So we can say that the maximum of the function, maximum of f, on the interval negative 1, 3 is, and is attained, is the value of the function at negative 1, which is equal to 10. And it happens at x equals negative 1. Okay, and similarly, the minimum of f on this interval, we can see that it happens at 2, right? So it's the value of the function at 2, which is actually 1, and this happens at x equal 2. Okay, so of course, if you have the graph of the function, this is a very straightforward and easy question to answer. But really, the question is, could we have figured this out from the formula alone without having to rely on the graph? Okay, and this is what we want to analyze. So some things here, uh, let's try to see if we find something that will help us figure out this information without having to rely on the graph. So first of all, notice that one of these values, in this case the maximum, happened at the endpoint of the interval. So it happens at -1, which is the left endpoint of the interval. Okay, so that means that if you're looking for absolute extrema on a closed interval, that you need to consider the endpoints as your candidates. Okay, and then also notice that that's not the only case. That's not always the case. For example, we found a minimum at x equal 2, but 2 is inside the interval. Okay, but what's special about x equal 2? Notice that at x equal 2, we have a horizontal tangent line, right? So here we have a horizontal tangent line. So that means that f prime of 2 is equal to 0. So that means x equal to is a critical point. Okay? So the moral of the story here is that maximums and minimum on a closed interval, they may show up inside the interval or at the endpoints. But when they show up inside the interval, if they are a maximum or a minimum, then that means they are actually a relative maximum or minimum. And therefore, they have to be a critical point. Okay? So how is it that we're going to look for absolute maximum and minimums of a function? We're going to look for the candidates. The candidates are going to be the critical points inside the interval and the endpoints of the interval. You have to include the endpoints as well. And then once you have that list of candidates, all you have to do is evaluate the function, plug in these numbers into the function. Whichever is the highest is your maximum. Whichever is the lowest is your minimum. Okay? So just like that. That's how we're going to find maximum and minimums. So let's do some examples. Okay. So for example, so note, let me just, for this same problem, let's do what I just told you so you can see how we could have find this, how we could find this without having to rely on the graph. So to find these values without the graph, we list, we list candidates, and they are the critical numbers, so critical points, because they happen inside the interval, and also the endpoints of the interval. And this, of course, is critical points in the interval. If you have a critical point that is outside the interval, we don't care about it. Okay? Then endpoints of the interval, and then evaluate and pick the max and min. Okay? So let's do it. So we have f of x, which is equal to x squared minus 4x plus 5. So let's first find our critical point. So for that, as you know, we need to find the derivative. That's 2x minus 4. And then we need to analyze what happens when the derivative is undefined or 0. Over here, we don't get anything because that's a little polynomial. On derivative equal to 0, we just solve this little equation, and that means that x is equal to 2. Okay? So that means that our candidate, remember the interval was -1 to 3. So x equal to 2 is a critical point. So we're going to have here our list of candidates. So the candidates are going to be 2, right? That's our critical point, and then -1 and 3, because those are the endpoints of the interval. Those are our candidates. And now here we're going to evaluate. So f of x, which is x squared minus 4x plus 5. So let me just write f of x. Okay, so let's find the value of the function at 2, the value of the function at -1, the value of the function at 3. So the value of the function at 2, as you know, is going to be, what is it? You plug in 2, you get 4. I mean, we can see it above, but let's do it without looking at the picture. So f of 2 is equal to 4 minus 8 plus 5. So it's going to be 1. Then f of -1 is going to be 1 plus 4 plus 5. So that's 10. And then f of 3, that's 9 minus 12 plus 5. So what is this? -3 plus 5, that's equal to 2. Okay, so now we look at the y values, and then from here, from this list, we need to select what's the maximum and what's the minimum. Well, it's clear that the lowest value is 1. So this right here tells us that we have found a minimum, and then the highest value here is 10. So this right here tells us that we have found a maximum. Okay, so this is how we find maximum and minimums on a closed interval for a continuous function. So find your candidates. Your candidates are going to be critical numbers and the endpoints of the interval. Then just go plug in each of those points into the function, and whichever is the highest number, the highest output, that's your maximum. The lowest output, that's your minimum. Okay. All right. So let's do some examples. For example, for this, so let me summarize the steps, which are exactly the ones that I just mentioned. So to find extrema of f on a closed interval, we may follow the following steps. So step number 1, find, well, you need to find f prime, right? So find f prime, you need to find the derivative. Then step number 2, find all critical numbers. Find all critical points of f inside the interval AB. Remember, by solving either f prime equal to 0 and finding values that make f prime undefined. Don't forget that critical points are those that make the derivative equal to 0 or undefined. So after you do this, then write your list of candidates. So list of candidates, and these are all critical points found in step 2 and also the endpoints of the interval. Okay, which in this case would be A and B. Okay, and then once you have your list of candidates, step number 4 is evaluate each of the candidates in the function. The highest number is the maximum, the lowest number is the minimum. Evaluate each candidate. In F, and the largest number is the maximum, and smaller number is a minimum. Now understand that this may happen more than once, so the maximum and minimum may happen at different locations, but the actual number, the actual value is only one, okay? The actual maximum and minimum is only one number, but now the location may happen at different places, okay? Okay, so that's the idea. These are, it should be pretty straightforward to follow these steps. So let's go ahead and let's do examples. So here we have some functions, and let's go ahead and let's find the string values of these functions on the given closed interval. Notice that all of these functions are continuous, so they have a maximum and they have a minimum on the given interval. So let's find them. All right, so solution. Let's see, for the first one we have f of x equals 3x to the 4 minus 4x cubed, and then the interval is negative 1 comma 2. So the first thing that we're going to do is to find the derivative, because we need critical numbers. So derivative is 12x cubed minus 12x squared. Now, as you know, the derivative is never undefined. So if prime undefined, we don't get anything from here. Okay. So now if prime equals 0, that means that we need to solve this equation. We can factor this, so we can take out 12x squared, and then we get an x minus 1. And so from here we get two solutions, x equals 0 or x equals to 1. Okay, and notice that both of these guys, they are inside the interval in question, which is negative 1 to 2. So we want to use both. So now we do a little table with candidates, and then the y equal f of x. We'll find the y value of these numbers. Okay. All right. So what are the candidates? The candidates are gonna be 0, are gonna be 1. Okay, those are the ones coming from the fact that the derivative is equal to 0. Those are the critical numbers, and then we have negative 1 and we have 2. So again, these top candidates are coming from critical numbers. The bottom candidates, these are the endpoints that they always have to be there. Okay. All right. So now it's just a matter of plugging in and then determining which one is the maximum and which one is the minimum. That's it. All right. So let's see. F of 0. What's the value of the function of 0? Well, that's just 0. So that's going to be 0. Then so remember that the candidate, okay, so let me write here f of 0 so it's clear. So f of 0 equals 0. Then we want to find f of 1, f of negative 1, and f of 2. Okay, so what's f of 1? That's going to be 3 minus 4. So that's a negative 1. Then f of negative 1, that's going to be 3 plus 4, because the second one survives the negative. So that's a 7. And then f of 2, what is this? So f of 2, so also be careful. Make sure that, notice that you need to plug in into the original function f, not in the derivative, okay? So we are plugging in here, so be careful. Don't plug in the wrong place. Okay, then f of 2 is going to be 3 times 2 to the 4 minus 4 times 2 cubed. So 2 to the 4, 16. So that's 48. 3 times 16 is 48 minus 2 cubed is 8. 8 times 4 is 32. So what is this? That's 16. So this is equal to 16. Okay. So now with this information, we look at it and then we see that right here, This is the lowest value. So we have found ourselves a minimum. And then right here, this is the highest value. So we found ourselves marked a maximum. So f has a minimum of -1 at x equal 1. F has a maximum of 16 at x equal 2. Okay? All right. So that was the first one. Let's do the next one. So the next one is slightly more interesting because now, the algebra becomes, uh, a little bit more interesting. And then the third one is we're going to need to do some trigonometry. So that's a good exercise. All right. So let's do B. So 2x minus 3x to the 2/3. So 2x minus 3x to the 2/3. And then the interval in question is -1 to 3. So notice that the function is continuous on this closed interval, so it will have a maximum, it will have a minimum. So let's activate the process. So f prime is going to be equal to 2 minus 3 times 2/3 x to the 2/3 minus 1. Simplifying this, we get 2 minus 2 x to the -1/3. Now remember, negative exponents are very misleading, so let's get rid of this by writing this as 2 minus 2 over x to the 1/3, and then let's combine. Okay, so the LCD is x to the 1/3. So here we have 2 x to the 1/3 minus 2. So make sure that you guys understand how to do this, okay, that you know how to go from here to here, okay, that you understand how to subtract fractions when there are variables and multiple expressions appearing, okay, because you will have many situations in which you need to do this, and you don't want to lose points, stuff like this. Okay, so then because we need to find zeros, remember you should factor as much as you can. So in this case, I can take out 2, and then we get x to the 1/3 minus 1 over x to the 1/3. Okay, so now we're gonna find the critical numbers. So for that, remember we're looking now for critical numbers. So they will come from two places where the derivative is undefined and where the derivative is equal to 0. So this time we do see the derivative is undefined at x equals 0 because that makes the denominator equal to 0. Okay, so that's a point that we need to consider. So this guy here, and then f prime equals 0, that comes from the top. Remember, this means that the derivative must be 0, so it's a fraction, so the top has to be 0. So we get 2 times x to the 1/3 minus 1 over this guy equals 0. That means the top must be 0. So that means that x to the 1/3 has to be 1. Therefore, x is 1. Just cube both sides. Okay, so we found two critical numbers. Okay, and by the way, notice that in the previous example, the minimum was found in the critical numbers and the maximum was found on the endpoints. Okay, so if you don't find critical numbers, you would have missed the minimum. If you don't consider the endpoints, you would have missed the maximum. Okay, so we have our candidates for this one. So now let's write them down and figure out. So candidates and their values. Let's see. So we found 0, we found 1, and by the way, notice that both 0 and 1 they are inside the interval -1, 3. So we're good. Then the endpoints is -1, and that's 3. Okay. So let me write down the formula here so it's easier to plug in. So I don't have to be scrolling. So 2x minus 3, x to the 2/3. Okay, so what's the value of the function at 0? So f of 0 is 0. What's f of 1? F of 1 is 2 minus 3. So that's a negative 1. F of negative 1, that's a negative 2 minus 3 times negative 1 to the 2/3. So notice that when you do negative 1 to the 2/3, that becomes positive 1 because ultimately you're doing a square. Okay, so that would be negative 2 minus 3, that's negative 5. And then f of 3, that's going to be 6 minus, let's see, 3 to the 2/3 times 3. Okay, that's 1 plus, so that would be 3 to the, so what is this? So 3 to the 2/3 times 3, that's 1 plus 2 over 3, so that's going to be 5 over 3, which is the fifth root of, which is the cube root. Yeah, no, it's just easier to write it as 3. So 3 times the cube root of 3 squared, which is 9. Okay. So, at this point you could just use a calculator, but let's see. So first of all, the cube root of 9 is less than 3. So that means that this number is positive. So we definitely have already our our lowest value. So our lowest value is found here, which is negative 5. Okay. So now, because the remaining ones are negative 1, 0, and then add 3. So note the cube root of 9. This is definitely bigger than 2 because cube root of 8 is 2, but it's less than 3 because cube root of 27 is 3. So if I multiply by 3, so multiplying everything by 3 times 3, actually, yeah, no, actually it's going to be negative. It's not going to be positive. So wait, let me not be too quick here because we're not done there. Okay, so multiplying everything by 3, we get here 6 is less than 3 cube root of 9 minus 9. Again, if you just put in a calculator, you will know, okay? I just want to see what what we get here. Okay, so the point is that this number is bigger than 6, so that means that f of 3 is less than 0, okay? Now the question is it less than negative 5? Well, if this would have been 27, okay, so no, negative 5 is lowest. So let me show you why. So f of 3 is less than 0. Move this over here. It's just that, I don't want to rely on the calculator if we don't have to, because here we don't really want the exact value unless we found an extrema here, but we can actually analyze it. So f of 3 is less than 0. Also, notice that the cube root of 9 is actually less than the cube root of 27, right? Which is equal to 3. So what this means is that because this number is less than 3, then 6 minus 3 cube root of 9 is going to be greater than 6 minus 3 times 3. So let's see. Let me explain this. Okay, so because this number, or let me do it from the other way around. Because this number right here is bigger than this one, because cube root of 27, which is 3, okay, is bigger than cube root of 9, then that means when I multiply by 3, then of course, if I multiply this by 3, I get that this is less than 9, okay? I get that this is less than 9 because multiplying both sides by 3, because 9 is bigger. If I do 6 minus 9, I'm gonna get a smaller number because, 9 is bigger, so you're subtracting more from 6. So that's why 6 minus 3 times cube root of 9 is actually larger than 6 minus 9, which is negative 3, okay? So the point is that this number here is bigger than negative 3. You could just find it in your calculator, okay? I repeat, so don't worry too much about this. This is just me not wanting to use a calculator. So the point is that this number is bigger than negative 3, so negative 5 is indeed lowest, okay? So now we're sure that this guy is a minimum, but notice that f of 3 is less than 0, so that means that the maximum in this list is actually 0, because the other values are negatives. So here we have our maximum, okay? So the maximum of the function is 0, and it happens at x equals 0. The minimum of the function is negative 5, and it happens at x equals negative 1. Notice, okay, so once again, one of the values was found in the interior of the interval, so it was a critical number. Another value was found at the endpoint, okay? And by the way, notice that the maximum here, which is 0, happened to be, it's a critical number, but it's a critical number coming from the fact that the derivative is undefined. So, if when you're finding critical numbers, if you only look at values that make derivative equal to 0, and you forget or avoid those that makes it undefined, you would have missed this, okay? So keep that in mind. So it's important to consider both types. Okay, so that was B. Now let's do C. Mhm. Okay, wait, slow down. Okay, so 2 sine minus cosine of 2x, and this is happening on the interval from 0 to 2 pi. So 2 sine minus cosine of 2x. And we want to do this from 0 to 2 pi. Okay, so again, this function is continuous. So on this closed interval, it's going to have a maximum, it's going to have a minimum. All right, let's find critical numbers. So take derivative. So derivative of this is going to be 2 cosine, and minus derivative of cosine is negative sine. So now here we need to use chain rule because of the 2x, okay? So negative sine of 2x, and times derivative of 2x, which is 2, okay? Remember the chain rule. So composition, you need to multiply by the derivative of the inside. Okay, so we get 2 cosine of x plus 2 sine of 2x. Now, before I continue working here, I want to factor this. Now, and it's not nice that we have a mixture of cosine and sines. So if we could do something about this, then we should do it. And here I'm gonna use an identity. Okay. So right here we have sine of 2x, and then recall. Let me write it here. Recall sine of 2x equals 2 sine of x times cosine of x. That's the double angle formula. Okay, so I'm going to use it. So we have 2 cosine plus, and then when we use that, we're gonna get 4, because we already had a 2, so 2 times 2 is 4. 4 sine times cosine. And this then allows to factor, so we can take out a 2 times cosine, and then we get 1 plus 2 sine. And so now we can easily solve this. Okay, so again, f prime undefined. This time it's not gonna give us anything because this is defined everywhere. So then f prime equal to 0. This time we do need to solve. So we get this equals to 0. So from here it follows that either cosine of x is 0 or sine of x is negative 1/2. Okay. Okay. So once we get, now we solve these two little equations. Remember, we need to solve it inside the interval from 0 to 2 pi. So when is cosine equal to 0? All right. So this happens when x is pi over 2 or 3 pi over 2. That's when cosine is equal to 0 inside the main period, 0 to 2 pi. And then when is sine of x equals to negative 1/2. Okay, so that's going to happen in quadrant. So we're going to have an answer in quadrant 3. And we're also going to have an answer in quadrant 4, right? Because remember, sine is positive in first and second quadrant, is negative in the third, fourth quadrant. So what will be the x's here? So the reference angle is what angle give you 1/2. So the sine of what give you 1/2? That's 30 degrees or pi over 6. In quadrant 3 is going to be pi plus pi over 6 using the reduction formulas. In quadrant 4 is 2 pi minus pi over 6. So no coterminals here. You don't have to do plus 2k pi, nothing like that, because we are restricting ourselves to the interval from 0 to 2 pi. Okay, so this would be 7 pi over 6, and then 12, so 11 pi over 6. Okay, so we found ourselves 4 candidates. Okay, so 4 critical numbers, and then of course together with the endpoints. So let's put it here. Candidates is gonna be a bigger table now, and then we have here y equals f of x, and remember the function is 2 sine minus cosine of 2x. Okay, let's put the candidates. So that's pi over 2, then that's 3 pi over 2, 7 pi over 6, 11 pi over 6, and then we have the endpoints, which are 0 and 2 pi. Okay, now we plug in, and then we'll be able to tell what's the maximum and what's the minimum. Okay, so f of pi over 2. So remember, sine of pi over 2 is equal to 1. So that's 2 times 1. And then here we get cosine of pi. When you plug in pi over 2, that's a negative 1. So minus minus 1. Let me write like this. So it will be 2 plus 1. So it gives me a 3. Okay. So 3 pi over 2, what do we have? Now sine is negative 1. So that's 2 times negative 1. And then we get cosine of 3 pi. And once again, cosine of 3 pi, that's the same thing as cosine of pi. So as another negative 1. Because when you put 3 pi over 2, the 2's cancel. So you get cosine of 3 pi, which is also negative 1. So negative 2 plus 1, that's negative 1. All right, so 7 pi over 6. So it will be 2 times. So remember, this at the 7 pi over 6 was the value that gave us negative a half for sine. Okay, so times negative 1/2 minus, now that will be cosine of 7 pi over 3. Okay, let me compute that here. So cosine of 7 pi over 3. So this is more than 2 pi. We can do 6 pi plus pi. So this is the same thing as, this is coterminal with pi over 3. So this is cosine of pi over 3, which is 1/2. Because 7 pi over 3, you can write it as 2 pi plus pi over 3. Okay, and so that's why it's coterminal to pi over 3. So that would be cosine 7 pi over 3 is 1/2. So minus a half here. So we get negative 1 minus 1/2. That's negative 3/2. Negative 1 minus a half. Yes, negative 3/2. Then put 11 pi over 6. What do we have? Again, negative 1/2 here. Minus. So we're gonna get 11 pi over 3. So what's cosine of 11 pi over 3? So when you multiply by 2, the 6 cancel and you get a 3. Okay, so similarly, let's see. This is 6, 11 is 6 plus 5. So you can think of this as 2 pi plus 5 pi over 3. Okay, so this is the same thing as cosine of 5 pi over 3. Now 5 pi over 3, this is 300 degrees. So this is more than 3 pi over 2. So because it's 5 times 60, so it's 300, more than 270. So this is in quadrant 4. In quadrant 4, cosine is positive. So this is going to be positive 1/2. So now here we do get negative 3/2 again, because it will be negative 1 minus a half. Then f of 0 is going to be 2 times 0 minus 1. So it's going to be negative 1, because cosine of 0 is 1. And then f of 2 pi, we should get the same thing. So that's going to be, what is it? Sine of 2 pi, that's also 0. And then cosine of 4 pi, that's also 1. So we get negative 1. Okay, so we found all the values. Then looking at this table, it's clear that the highest value is this one. So this is our maximum. And then the lowest value is negative 3/2. But notice that negative 3/2 showed up at 2 places. So we have a minimum, but the minimum actually showed up at 2 locations. So we have a maximum. The maximum is 3, and it happens at x equals pi over 2. The minimum is negative 3/2, but it happens at 2 places, at x equals 7 pi over 6 and x equals 11 pi over 6. Okay, so remember, the maximum and minimum, they may show up at different locations. The value is 1, it's only one value, but the places at which they appear, they may show up at multiple places. Okay, so that's how you find maximum and minimum values. So hopefully with all these examples, you will be able to, now with this you can do every problem on the homework that has to do with finding absolute extrema. Now, we still have the question of how do we find relative extrema? So how do we find relative maximum and relative minimum? So let's address this question now. And to be able to have a way of finding this, we need to talk about the first derivative test. But before we can discuss this, And we need to talk about monotony of a function. So how do we detect when a function is increasing or decreasing? We already have mentioned this before, and as you know, the information about increasing or decreasing is encoded in the derivative of the function. The derivative is going to tell us whether a function is increasing or decreasing. So let me remind you of the definition for this, okay? So what does it mean for a function to be increasing or decreasing? So let y equal f of x be a function defined on an open interval. Okay, defined on an open interval I. So we say that f is increasing on the interval I. Now, and what's increasing? You know, in common terms, increasing just means that the graph is going up, right? So just draw a little picture here, and we kind of talk about this once. So increasing means, you know, the graph is going up. Let's say that here you have point x1 and here the point x2. To say that the graph is going up is to say, you know, here going up means from left to right, because if you look at it from right to left, of course, it's going down. So, but you always read from left to right. So to say that we go from left to right is to say for any 2 points, x1 less than x2, that means we're going from left to right. Then what does it mean to go up? It means that the y value of x1 has to be less than the y value of x2, as you can see here in the picture. Okay? So to be increasing on an interval, this happens for any two if for any 2 points x1 is 2 in I. So whenever you pick 2 points, then you know one is less than the other one. Okay? So if x1 is less than x2, then f of x1 has to be less than f of x2. That's what it means to be increasing. As you go from left to right, this is a way of saying that as you go from left to right on the x-axis, you go from bottom to top on the y-axis. Okay? Now, similarly, we say that f is decreasing on an interval I. Now, remember, decreasing means the graph is going down. So let's look at the picture. Let's say that we have something like this. So this time, as you go from left to right, so for any 2 point with x1 less than x2, what happens is that the y value of x1 is going to be larger or bigger than the y value of x2. So as you go from left to right on the x, you go from top to bottom on the y. Okay, so the values of the functions, they get smaller as the input increases. So if for any 2 points x1 x2 in I, we have that if x1 is less than x2, then, so now the other way around, f of x1 has to be bigger than f of x2. Okay, so that's what it means to be decreasing. And then just for completeness, if the function is neither increasing nor decreasing, we call it constant function. Okay, so we say that a function is constant on an interval if for any 2 points the value of the function are the same. So in the picture, so how does a constant function looks on an interval? Well, it's just, you know, the horizontal line, and then no matter what x1 or x2 you pick inside that interval, the value of the function are the same. Okay, so here we see that f of x1 equals f of x2. Okay, so we say that f is constant on an interval I if for any 2 points, x1, x2 in I, we have that f of x1 equals f of x2. So that's what it means for a function to be constant. Okay. So now what we want really is to be able to determine this behavior, of course, from the formula, right? Now the thing is that this definition, this is the precalculus definition, and this is the definition of increasing, decreasing, constant. However, it may not be that straightforward to figure this out, because solving inequalities in general is not an easy job. Okay, and to argue these type of inequalities for an arbitrary function, the formula could be complicated, and then this may not be easy. So we want to find something that may help us figure this out a little bit easier. So the question is, how do we detect the monotony of f from the formula without having to rely on the basic definition? And as you know, the answer lies in the derivative. Okay, so let me write that down, but before that, let's do a little exploration. Even though we have been talking about this, let's do a little exploration here. So the question now that we want to answer is, how do we detect the monotony? So increasing, decreasing is called the monotony of a function in general. Okay, how do we detect the monotony of f from this formula? Okay, so if you have the formula y equal f of x, how this can help us find the derivative, and then how can this help us detect what's going on with the function? The point is, let's take a look at some situations. For example, here is a situation in which the function is increasing. Here is situation in which the function is decreasing. And then here is a situation in which the function is constant. So of course here is increasing, here is decreasing, and here is constant. And then what we can say in each of these situations, of course we have the definition above. For example, we can look at the slopes. Notice that in this case, when the function is increasing on an interval, if you pay attention to the slope at any point on that interval, the tangent line always have positive slope. So that means the slope is positive. Okay, which means that the derivative is positive. Okay, similarly, on a similar note, for the decreasing case, if you look at this at any point and you look at the slope of a tangent line is going to be negative. So here slope is negative, therefore derivative is negative. And in the case of the constant, notice that the slope equals 0, right? So derivative equals to 0. And this right here is the criterion that we're going to use to determine whether a function is increasing or decreasing. So the information lies in the sign of the derivative. Whenever the derivative is positive, on that interval the function is increasing. If the derivative is negative, then the function is decreasing. Okay, so that's what this theorem is saying, and then hopefully this is straightforward to understand why. Remember, derivative is a slope, so, and you can detect going up or down by looking at the slopes. Okay, so suppose that we have a function, so let f be a function. Now this function has to be differential, okay, continuous and differential. Let f be a function that is continuous on the closed interval ab and differentiable on the open interval ab. Then Then we have some statement. So number one, if the derivative is greater than zero, so if the derivative is greater than zero for all x in AB, then the function is increasing on that interval. If the derivative is negative for all x in AB, then f is decreasing on this interval. And then condition number three is that if the derivative is zero on the entire interval, so if it's equal to zero for all x in the interval, then the function is constant. Okay, then f is constant on AB. So the monotony information of a function is encoded in the sign of the derivative. Okay, the first derivative has all the information regarding the monotony of the function. Now I'm writing this theorem for intervals of the form a comma b, but this also applies for other type of intervals like half open, half closed, and an entire real line. So let me write that down. So this theorem applies to any interval on which f is continuous and differentiable. Okay, as long as f is continuous and differentiable, then we are good. Like for example, maybe the interval has this form a comma positive infinity or negative infinity comma b, or maybe the entire real line, etc. Okay, it's just that I'm using a comma b, but it doesn't have to be necessarily like that. Okay, so you could have some infinities in there and so on in the interval. Okay, so of course the challenge in doing this is being able to establish these inequalities. Okay, so the question is, how do you solve inequalities? So remember, if it's a linear inequality, it's straightforward. You have been doing that from a long time. Now, what if typically what you're gonna have is a non-linear inequality? Okay, and you kind of learn in pre-calculus a systematic way of solving nonlinear inequalities when you discuss polynomial and rational inequalities. But the same idea applies to any other function. The way that we solve nonlinear inequalities is we find the zeros of the function, the values that make the function undefined. Okay, we put all of those numbers on a line, and then we test the function for sign. We just plug in, pick a point in each of those intervals and plug it in to determine if the function is positive or negative. And I'm going to be doing this in every single example that we're going to do. So hopefully by the time we're done with these examples, you will understand how to do this. Because I know that in pre-calculus sometimes, this general procedure is sometimes a little bit overlooked. And then you only focus on polynomials and rational functions. But you need to realize that those same ideas can be extended to any other function. Okay? All right. So let's do examples to see how we can find this. So examples, and here is determine the open intervals on which the function is increasing, decreasing, or constant. The monotony. or constant, and give the answer using interval notation. So answer with interval notation. Okay. Oh, let me write the full word with interval notation. And then let's see, f of x equals x squared minus 4x plus 3. Start with something simple. And let's do x cubed. Now let's move to something more interesting. 3x to the 4. So 1 and 2 are our sanity check examples. Okay. 3x to the 4 plus 4x cubed minus 12x squared plus 2. And let's do x times square root of 16 minus x squared. And then let's do f of x equals x minus 2 cosine. And here let's just focus on the interval from 0 to 2 pi. Okay, so inside that interval, let's find when it's increasing, when it's decreasing. All right, so once we do these examples, then you should have a good understanding of how to solve nonlinear inequalities. Okay, so solution. So remember, to find the monotony, what we want is to investigate the sign of the derivative. So for the first one, we have f of x equals x squared minus 4x plus 3. So because we want the sign of the derivative, of course, we have to look at the derivative. So derivative is 2x minus 4. Now here, be very careful, okay? And when we analyze the sign, is the derivative, so you have to work with the formula for the derivative, okay? So let me factor this. So now it will always be the same thing. So I'm gonna draw a line here, okay? So you need to find the zeros of the function, okay? So let me guess, write it down. So zeros is x equal to undefined, none. Okay, so now here we are analyzing the sign of f prime. I'm doing red. The sign of f prime, and to do that, you put a number line and then you put the values that you found, the zeros and the values, and make it undefined. In this case, there is only one, which is 2. Okay, so that means the real line is split into two intervals. Okay, less than 2 and bigger than 2. Okay, and now how do you determine the sign of the function? This one is a linear inequality, so you could do it easily, but in general, this is the procedure. Pick a point in each of the interval and plug it in, and then record the sign. For example, to the left of 2, if you pick, I don't know, the easier one is x equals 0. If we pick x equals 0 as our test point, when you plug it into the derivative, you're going to get a negative value, right? So that means derivative is negative. So I'm going to put a minus in here. This minus means the derivative is negative. Okay? To the right of 2, pick a point, let's say 3. You plug it in, you're going to get positive. So I'm going to put a plus in here. That means my derivative is positive. So now, what's the monotony? Well, the function is decreasing over here because the derivative is negative, and the function is increasing over here because the derivative is positive. You're gonna see me doing pictures, little graph like this a lot. Okay? Alright. So because we're gonna take up with the arrows and all of that, because we're gonna take advantage of this later on for something else. Okay? Alright, so the conclusion is, where is the function increasing? The function is increasing on the interval from 2 to infinity. That's where the arrow is going up, right? That's where the derivative is positive. Then the function is decreasing from negative infinity to 2. and then constant, none. The function is never constant. Okay? All right. That was one example. And I said it was sanity check because, this is a parabola, so we can easily figure this out. So let's find what's the vertex. As you know, this is a parabola that opens up, right? It does this. So here is the vertex. So it's going to be decreasing to the left of the vertex and then increasing to the right of the vertex. So let's see, what's the vertex here? The x of the vertex is negative b over 2a, which would be negative 4 over 2 times 1. So that's 4 over 2, which is 2. So indeed, this point is 2 comma f of 2, whatever that is. The point is that to the left of 2, the function is decreasing. To the right of 2, the function is decreasing. And that's exactly what we found. Okay? So that's our little sanity check. In other words, what we are saying here makes sense. Okay? Let's do another one. Let's do f of x equal x cubed. That's our second example. For example, in this case, what sort of answer are we expecting? As you know, x cubed is a function that's always increasing. So we should get that it's decreasing everywhere, it's increasing everywhere and never decreasing. Okay? Well, let's see it. Well, in this time, when we find the derivative, that's 3x squared, right? So again, zeros, and just x equal to 0, undefined, none. So the sign of f prime, you put here your number line, so we only found 0. And then because we have 3x squared, you know that 0 has even multiplicity, that's always positive, right? That's positive, that's positive. So it means the function is increasing in both cases. So increasing negative infinity to positive infinity, and then decreasing non-constant, none. Again, we expected this, we knew this already. So now let us look at something that we don't know, right? At least that we don't know a priori. Something more interesting, like our degree 4 polynomial, 3x to the 4 plus 4x cubed minus 12x squared plus 2. Okay, so again, what we need to do, we need to find the derivative. So that would be 12x cubed plus 12x squared minus 24x, and that's it. And now if you can, you should factor because that's gonna make our life easier. So I can take out here 12x. So I'm gonna have an x squared plus x minus 2. Okay. And then once we get this, we factor. So let's see, we can do 2 and negative 1. So it's 12x and then x plus 2, x minus 1. Okay. So for the sign of f prime, so remember, we need to find the zeros and undefined. This is never undefined. So all we really care about are the zeros. And the zeros are negative 2, 0, and positive 1. Okay, that's where the derivative is 0. In other words, we're finding the critical numbers. Okay, we're finding the critical numbers. And then once you find these numbers, notice that the line now is split into 4 intervals. Okay, so all we have to do is test the function in each of these intervals. So let's see, I'm gonna pick negative 3 as a test point here. Over here, I'm gonna pick negative 1. I mean, you can do this faster using the multiplicity information of the polynomial, but if you don't want to deal with multiplicity, then you do this, but you should. I mean, that's why you study multiplicities in pre-calculus. So when you have polynomials, so you can do these problems quicker. Okay. So you already know the plugin business. Let me show you how to do it with multiplicity. You just need to find the first element, okay? The sign in the first interval, the one on the left. So let's see, when you plug in a -3, what do we get? So the first factor, you look at the factor version. So we're gonna have a negative times a negative times a negative. So as positive times negative, so the function is negative, okay? Now after that, notice that each of the zeros, they have multiplicity 1. So that means the function is gonna cross the x-axis at each of these points, meaning the signs alternate. So minus, plus, minus, plus. Now you can also try this by plugging in each of those points that we chose at test point, and then you will see that we do get the corresponding sign. So point is that here the derivative is negative, positive, and negative, then positive again. Okay. So the function is increasing on -2, 0, and also 1 to infinity. So in the homework, when you're doing this, and maybe they will expect you to write a union in here. Technically, if you look at the formal definition of increasing, we should not write a union because it could violate the definition. So that's why I put commas, okay? But it could be that the homework, if you get two intervals, they require you to write union. So if you do the problem and you put a comma and you get it wrong, then just write the same thing but with a union, okay? Just keep that in mind. And then decreasing will be -infinity to -2, and then it's also decreasing from 0 to 1. And well, constant is never constant. So constant, none. Okay, so it was slightly more interesting than the previous ones. Okay, so let's do number 4. Number 4 is f of x equals x times the square root of 16 minus x squared. Now remember, in the previous fun, you always need to have the domain of the function in mind. I didn't worry about that in the first 3 examples because we had polynomials, okay? And polynomials are defined everywhere, domains of real numbers. But here, now we see a radical, we have to be careful, okay? So let's find the domain of this function so that we know the restrictions that we're working with. Because we see a square root, that means 16 minus x squared has to be greater than or equal than 0, okay? So this is another little inequality which is nonlinear, and now we know how to solve them. Okay, so 4 plus x, 4 minus x. So let's draw the picture. We put the zeros. The zeros are -4 and 4, greater than or equal than 0. So the endpoints are solutions, and then pick points. So pick something left to a -4, like -5. You plug it in. That's a negative. So that would be negative times, for a -5, then negative times positive, so that's a negative. So you pick 0, that's a positive. Then you pick 5, that's going to be positive times negative, that's a negative. Now we want the greater than or equal than 0, so that means that the domain is this portion right here. So we are working with x between -4 and 4. Okay, so domain is -4 to 4. So whatever we do is going to be inside this interval. Okay, so let's analyze then the derivative. So we have f of x equals x times this expression. So to find the monotony, we need the derivative. So here we need to use product rule. Okay, so that's 1 times second function plus the first times derivative of the second. Now here we need to use chain rule. 1 over 2 square root of 16 minus x squared times derivative of the inside, which is -2x. Okay, so working here, we get the square root of 16 minus x squared minus x squared over the square root of 16 minus x squared. So now let's combine this. Remember what I told you earlier? You need to be comfortable combining expressions like this. Right, so we get 16 minus x squared minus x squared, and then that becomes, so f prime of x equals, so 16 minus 2x squared over this. So we can factor out 2. So we get 8 minus x squared. Okay, and then let's take it a step further. Now the roots here are plus or minus 2 square root of 2, right? So that would be 2 square root of 2 plus x, 2 square root of 2 minus x. Okay, so now we can write the sign. So sign of f prime. So remember, the values that makes it undefined are positive, actually positive and negative 4, and they are part of the domain, so you should be considering those. So but because they are the endpoints of the interval, it doesn't matter because we're looking for the, for the interval of increasing or decreasing. So we have here negative 4 and 4, but we don't care about those because those are the endpoints anyways. There is no graph to the left or right. So that's fine. And then we do have some interior values. That's plus or minus 2 square root of 2. So as over here is negative 2 square root of 2. And over here we have 2 square root of 2, which are the zeros of the derivative. So now let's figure out the sign. So let's see, negative 2 square root of 2. If we pick something less than that, so that's gonna be, okay, so this is negative square root of 8, right? 2 square root of 2 square root of 8. The square root of 8 is less than 3. So negative 3 is definitely here. So my test value would be negative 3. So if I put a negative 3, then we're gonna have a negative in the top times a positive, and the bottom is always positive because it's the square root. A square root is always positive. So that's a negative. Okay, so it's a negative here. Now on the other interval, the easier one to pick is 0. If we plug in 0 into the function, we're gonna have positive times positive, so on top, so that's a positive. And then over here, let's pick x equal 3. Okay, 3 is bigger than square root of 8. And when you do that, we're gonna get positive times negative over positive. So that's a negative. Okay, that means the function is decreasing here, it's increasing here, and then decreasing. So increasing, the function is increasing from negative 2 square root of 2 to 2 square root of 2, then decreasing from negative 4 to negative 2 square root of 2, and then again from 2 square root of 2 to 4. Okay, all right, and then let's see, we have one more example to address, which is a little trick example. So let's do it. As f of x equals x minus 2 cosine. Okay, and here we are interested in x from 0 to 2 pi. Okay, between 0 and 2 pi. All right, so let's find the derivative. So we have 1 minus 2, derivative of cosine is negative sine. So we get 1 plus 2 sine of x. So we need to undefine. This is never undefined. So remember, we have to figure out when this is equal to 0. We need to find the 0. So for that, we need to solve this equation. So that means sine of x is negative 1/2. And we actually already solved this, right? So we have a solution in quadrant 3, and we have a solution in quadrant 4, namely 7 pi over 6 and 11 pi over 6. We did this problem earlier. We solved this little equation. So let's figure out the sine. Sine of f prime. So let's see. We have here, so what's our function? So let me write down f prime so we don't get confused with the original one. So remember the derivative is 1 plus 2 sine of x. Okay. So we are interested in the interval from 0 to 2 pi. So I'm going to write here 0, 2 pi. And because we're looking for interval increasing and decreasing, you know, there are always open intervals anyways. Doesn't make sense to have a closed interval. If you write it, it's not wrong, but it's also, there's no need to do that because, you know, at a point itself, the function is neither increasing nor decreasing. So that's why I'll be writing open intervals. And then we have in here, we have 7 pi over 6, then 11 pi over 6. Now, if we want to analyze the function in this interval, the sign of the derivative in this interval, there are many ways to do this, right? Just pick points and plug in. But let's see, we can do this very easily because this is the same thing as comparing, you know, sine versus the line negative 1/2. So whenever the sine is above the line negative 1/2, right? If sine is bigger than negative 1/2, then that would mean that the derivative is going to be positive. And then whenever the sign is below the line negative 1/2, that means the derivative is negative. So note the derivative, which is 1 plus 2 sine of x greater than 0, is the same thing as saying that sine of x is bigger than negative 1/2. Okay? And then similarly, less than 0 means that the sign will be less than negative 1/2. So we can quickly graph both of these functions and then see what's going on. So for example, if this is 2 pi, then the sign, as you know, let's say this is 1, this is negative 1, the sign begins here, then up here, middle. So middle, then down, then back up. So as a sine function, this is pi over 2, and then 3 pi over 2. So then 11 pi over 6. What is 11 pi over 6? 7 pi over 6, that's quadrant 3. So 7 pi over 6 is somewhere in here. Okay, so let's put it. It's more than pi, but less than 3 pi over 2. That's where the 7 pi over 6 is, somewhere in here. And then we have 11 pi over 6. Which is somewhere in here. So here we have 11 pi over 6. Okay, so that's the sine function. I put those points in there, and then let's put the line negative 1/2. So here is negative 1/2. Let's draw it. And as you know, the points of intersection are precisely this guy and this guy. So these points of intersection are 7 pi over 6 and 11 pi over 6. Okay? Okay, so now you can see that from 0 to 7 pi over 6, the sine function is above negative a half. So you get a plus. Between 7 pi over 6 and 11 pi over 6, the sine function is below. Here it is, right? It's below. So that means our function is negative. And then from 11 pi over 6 to 2 pi, that's the tiny little piece over there, the function, the sine function is again above the line, so it's positive again. So we get that it's increasing, decreasing, and then increasing again. So what is the function increasing? It's increasing from 0 to 7 pi over 6, and then again from 11 pi over 6 to 2 pi, decreasing from 7 pi over 6 to 11 pi over 6. And of course, it's never constant. Okay? All right. So with this, now we know how to determine when a function is increasing or decreasing. And this is going to be important for us when we want to graph a function. Okay? And right now, and just to close this discussion for today, and what I want to show you is that we can actually use this idea to figure out relative extrema. And let me take advantage of these same examples. For example, let's look at this one over here. And in fact, this one that we already know what it is. So notice that in this case, the value x equal 2 is a minimum. Okay, so this function has a minimum at x equal 2 because it's a parabola, right? And x equal to at x equal 2 we have the vertex and the parabola opens up, so we know it's a minimum. Now let's take a look at the behavior of the derivative around this point. Notice that to the left of the point the derivative is negative and to the right the derivative is positive. Now look at the sign that we have, the sign picture that we have, and look at the arrows that I draw. Now with your finger kind of, trace the movement of the arrows. And hopefully what you're doing now is this type of movement. Okay, so when you see this behavior, then it should be clear that what we have here is a minimum. So this right here would be what we call a local mean. Okay, because we have this sort of behavior. On a similar note, let's look at this one. If you trace the behavior, so what do we see? We see this behavior, then here we're gonna see this behavior and then this behavior. So the derivative changes from negative to positive around a point, that point will be a local mean. When it changes from positive to negative, what does that mean? It means it's increasing to the left and then decreases to the right. So what do we have? We have a local max. And then here, for example, we have a local mean again. This is what we call the first derivative test, okay? So now we know how to find local extrema as well. We discussed extreme, like absolute extrema on closed intervals before. Now we know how to find local extrema. We know the candidates are the critical numbers for local extrema, local maximum, local minimum. And now to find them, we can use the first derivative test, which is just look at the change of sign of derivative around the point. So let me write that down and then I'll stop here. We'll talk about concavity on Monday in class. Okay, so let me write this down and then do a couple of examples, but basically the same thing that we do to find the sign, the monotony of the derivative. Once you have that sign picture for the derivative, you can easily figure out the relative extrema, the maximum and minimum. Okay, all right, so let me write this down. So first derivative test, suppose that you have a function. So let y equal f of x be a function that's differentiable on an open interval I containing the point x equals c, except possibly at c. In other words, the function doesn't have to be differentiable at c itself, okay? But it must be defined. So, The function has to be defined. Okay. So then the condition is, the point is that if the derivative is negative for x less than c, okay, and if the derivative of the function is positive for x bigger than c, so that means to the left is negative, to the right is positive, then what does f has? Well, let's see, let's draw the picture. So we have here, so here is c, and then what we're saying is that the derivative is going to be negative to the left, is going to be positive to the right, so the function decreases over here and increases over here. So that means that we're going to have a relative minimum as a relative minimum at x equals c. So in other words, this happens if f prime changes from negative to positive around c. If changes sign around c from negative to positive. Okay, if that happens, then c is a relative minimum. Okay, then f of c is a relative mean. That's basically what we're saying here. Now, similarly, if it turns out that the derivative is positive for x less than c, so positive on the left, and then is negative for x bigger than c, so that means negative on the right, then what does the function has? Well, let's see. You draw the picture. Here is c. So derivative is positive here. Derivative is negative here, so that means increasing then decreasing. So we have a relative max at x equals c. So in other words, what we're saying here is that if f prime changes sign around c, but this time from positive to negative, then f of c is a relative max. Okay, so that's how we find relative extrema.